Hey everyone, I'm Steve Crusan. I've been using Lustre for quite a while, and the point of this presentation is kind of, I think, talk about some myths about small file performance and things like that on Lustre that I've heard throughout the community or just, randomly on the internet and things like that. Cool. So first, we're going to talk about who is HRT or Hudson River Trading, how we kind of use Lustre. Secondly, we're going to talk about some examples of myth-busting small file performance on Lustre. Some decisions for better metadata performance and scaling. Short Lustre wish list, and then let's get lunch. So who is HRT? I'm not going to go too much into who exactly we are, but we're a global, very successful quantitative trading firm. We trade on all markets, and we generally do everything. How we are in the computing space is that we're not really traditional HPC. So, we don't run large DOE style checkpoint, restart workloads, things like that. We do have demanding data needs, but it's not, I think, is the same as what maybe this audience is typically used to. However, if you think about like financial products and time series data, we're still doing sequential reads and writes and things like that. Our storage needs need to be flexible. We're not an MPI shop, so what that means is that all of our workloads are, I would say, if you were to think about it from an IT perspective, maybe like Slurm job arrays. So everything is supposed to be embarrassingly parallel, and tasks should be able to restart and do whatever they were doing successfully. So that means that some of the state of our job decks and all of our compute resources need to fall onto the file system. So it's not as easy as MPI ranks 0, sets up a directory structure, and then everything else follows afterwards. So there's a lot of logic that goes into our code that allows things to restart without issue. We also have a what I would call a user-friendly approach. So we have we have pipelines for jobs and all of that, and certain more productionized applications kind of have been well developed and things like that with a lot of user scrutiny. But also we allow users to open up a Jupyter notebook and just do whatever. And that anyone here knows that can be challenging, especially on storage systems when someone just has a crazy idea. Let's see what happens. HRT's been around for over 20 years. So before we were using Lustre, we just used a lot of NFS. So the firm is well aware of how NFS works, including like the cache consistency and coherence models. We have a lot of internal code that understands how NFS works, knows how to like basically clear out the caches and things like that though. So we're well aware of those sorts of things though. So Lustre was kind of new for us when we adopted it, I think maybe about 5 years ago. And lastly, as a firm, we do not like to use solutions that have a lot of downtime, meaning we don't have an opportunity to take an hour of downtime each month. We don't even have an opportunity to do that in a year. If we have to, then we'll do it, but generally we do not accept solutions that have to have that happen. I think within the last year, I updated all of our Lustre servers on one of our storage systems and rebooted them all at once for 10 minutes of downtime. That was kind of acceptable, but that's about it. So we're pretty big about those sorts of things. So how do we use Lustre? Lustre for us is a generalized scratch space. And when I say generalized, it means it needs to be able to meet all of the needs of anything that POSIX. So that could be a lot of bandwidth, whether it be sequential reads, sequential writes, a lot of IOPS, but we don't see that as much, or a lot of metadata operations. And that could be generalized namespace, writes, creates, things like that, or just a lot of namespace reads, which would be get adders, readers, things like that. But it generally has to support everything. Again, we don't really try to bring in storage systems that are overly specialized unless it's a very, very overly specialized workflow. So for instance, we have a favorite NFS vendor for something that does one little thing that it just does really well at. But for all of our generalized scratch storage systems, they need to be able to do pretty much everything pretty well. But as we all know, not all storage is equal, so I don't think anyone here is going to be surprised that Lustre is king at bandwidth. It hasn't changed in, 25 years. But also how we use Lustre is that the scalability and resiliency and resistance to heavy concurrency, meaning lots of concurrent tasks, CPU cores, et cetera, at scale, we've found that like most NFS systems cannot handle that very well. And as I said, performance does matter. We don't fit the typical profile of HPC, but we still do similar sorts of things. I feel like this slide is going to be a little controversial because this is going to sound crazy, but we use Lustre also as a tactical asset. And what I mean here is that on our other NFS-based systems, and these are not small systems either, so it's not like we have a 2-node NetApp and like we just beat it up and it falls over. Like we have pretty good sized NFS-based systems, and what generally seems to happen is some applications just completely destroy these systems. When I say destroy, I mean they fall over, they're not available for users, all RPCs are hanging, things like that. So, and again, this is gonna sound crazy, what we do is just tell people to run on Lustre. And not because it's some isolated thing where it's not gonna make anyone mad, it's just that there's a couple things here that most NFS systems don't have. Debugging power is a lot better. Even something as simple as job stats goes a long way. Also, per Lustre service, server side and things like that, also works very well because if for instance, this was a high concurrency to a single directory sort of workload, you would see one of the metadata storage servers just has a higher load and doing more operations. So there's a lot of tea leaves you can follow to analyze why certain workloads just don't really run well. And this is not available on most NFS systems. And also, Lustre, again, you log into the servers, or if you're troubleshooting a client side thing, it's just Linux. Everyone here is a good Linux IT person. You can just follow the tea leaves there. If you're not really sure what's happening, dump all the stacks and all the Lustre tasks and see what's going on there. You usually can start finding a pattern or something that is happening. And lastly, if you follow the WAM Cloud Jira, there's a lot of important or interesting information there, and someone has probably seen something that you're having an issue with too. So I think we've been a heavy DNE3 user, and when I say heavy, I mean as soon as the system was put in production, immediately pedal to the floor. But we've been like that since late 2021. I don't know of any other places that maybe hit it as hard as we did originally, but we've been just doing this for a while. There were some real world challenges that just are not going to show up in testing and everything else beforehand. And these things only happen when you do something at scale and something breaks. And this is a while ago, so don't take this as this is what happened now. But maybe 2 or 3 years ago, if we had a failover on some of your metadata targets, there's transaction logs that happen between all the MDTs for the remote makers. Going through those logs during the recovery phase, maybe that fails. Or maybe the logs get so massive that it takes 15 minutes to do failover. But those are all the sorts of things that we had to deal with, when I gave my presentation in 2022. And we don't really deal with that anymore because things have evolved a lot since then. So I'm going to go through some myth busting of real world examples of things that have happened on our systems that reinforce the idea that small files on Lustre is not a bad thing, and it's not true that Lustre can't handle it. So the very first one, first we're going to talk a little bit about some of these ideas. So where did the idea that Lustre is not good at small files come from? Lustre was not able to do active-active metadata for quite a while. If you compare it to other HPC or parallel file systems. And from an NFS standpoint, you have to be able to do parallel metadata because each client connects to a different server in an NFS cluster and things like that. So that always had to be there in NFS. Lustre was just a little bit late to the game, even though it was talked about for a while. So the common knowledge was that don't do small files on Lustre. And that was further reinforced by users would just overload MDT0. Every single person here has had to deal with this, and it stinks. but like that's just how things were. So how it was worked around for a while is that, you know, teams would just optimize code if you could, to just don't do a lot of metadata. And I think you should be doing that anyways, but for this, you know, specific thing, that's how you worked around it, is just don't do a lot of metadata. DNE1 was shipped in Lustre 2.4, so it was probably more finalized in Lustre 2.5, which was a LTS release. So that kind of laid the groundwork for distributed namespaces and better performance. However, like the adoption for beyond Lustre DNE1, I don't know how largely it was adopted. And this is in some of the other slides, but even when I worked for a storage vendor kind of architecting these sorts of things, not a lot of customers were really asking for like, oh, I need to do, you know, 4 MDTs versus, you know, of performance or something like that. Normally it was the standard, you know, buy 2 metadata servers with some storage behind it and active passive, things like that. Because generally, you know, you don't do small files on Lustre, right? That's why no one did anything differently. But again, laid the groundwork for DNE3. So some evolution of DNE3. DNE2 was introduced and to address highly concurrent directories. But again, I don't hear about a lot of adoption. I think it's a great feature, especially with the auto split stuff, because I can see certain situations where it's almost like PFL except for directories. And maybe some of that is that it just needs more love and care, and someone needs to beat it up a little bit, or, you know, harden the code, or work with WAM Cloud or something like that and improve it. But regardless, without DNE3, there was a lot of manual admin intervention in order to like balance your metadata capacity, allocations, and your performance. From a simplistic perspective, I think it makes sense, especially if you know that some user or some project is just going to really beat up a file system. So you can kind of isolate the trouble they make. But what happens is you just kind of create artificial hotspots, because if you have 8 MDTs and you just lock someone into one of those metadata targets, they can't use the rest of the performance. So basically their I/O performance suffers. You could tell them to fix the code again, which is the right thing to do, but you know, that's very optimistic, to say the least. So a couple more things. Some of the common pitfalls I've also heard about DNE before DNE3 is that some users, especially if they're less technical users though, didn't even know they had DNE or didn't know how it worked. So they would have 4 metadata servers or metadata targets, and they would only use the first one, and then a couple of years later, MDT0 is full, and all the other metadata targets, there's zilch on them. So part of it is things need to kind of just work out of the box for less technical staff, because if Lustre needs to have better adoption, you know, besides just HPC and the old adage is you need a PhD to run Lustre. Like, if you don't have those people, then things need to work a little bit better out of the box. But that's kind of like what we're getting towards. So, were the haters right in terms of is Lustre bad at small files and metadata? Historically, I think it's a true statement. It really wasn't a priority from what I can tell. I mean, I think people wish it could be better, but like I didn't see and there's investments in DNE1, but there wasn't kind of an investment to kind of tie it all together. And some of this might and some of this might be because we haven't heard a lot of presentations about it. Like I've seen presentations about DNE1 and the performance is nice for the IO500, but I haven't seen a lot of like this is the crazy stuff we're doing with metadata on Lustre. So I think some of the stereotype kind of perpetuated because of that. But today, even without DNE3, within the past 8 years, PFL and data on metadata, that makes a huge difference, especially if you're running spinning disk OSTs, so automatically that's way better. There's been a lot of metadata performance improvements just in the actual code, not DNE3 or the parallelism, like just follow, like WAM Cloud and HPE, et cetera, have been constantly making like the performance a little bit better. And lastly, like DNE3 kind of is a glue layer that adds the scaling for the performance and the allocations. So some examples of myth busting here. I think Livermore had 105 billion files though, so I guess this isn't really that nice of a number on one of their systems, but Lustre scales for handling lots of files. We've had over 25 billion files and directories on a single file system. And as you know, it's generally going to be the most problematic users or the users that are doing the craziest things. I didn't do any tuning for this, and of these 25 billion files and directories, if you look at the capacity and the inode usage on your MDTs, there was less than a 3% imbalance. And that's just me doing nothing. So out of the box, the code just works really well. And so there was no overhead. And how we deal with this now is that we expect 5 to 10 billion files per file system at a minimum, and that's pretty much what we have at all times. But like we plan for a lot more, because as we found, if users can more easily create files and you know, just run the file system like that, then they're going to do that. So you kind of have to plan for worst case scenarios. This same workload, it's not like the users pulled up a tractor trailer and teleported all those, you know, 25 billion files and directories into the file system instantly. Over time, over months, they were constantly creating these files, constantly creating these directories, and some of these, I think, parent or holder directories had like 100,000 entries in them, and they were always being updated though. So we saw a lot of like get adders, set adders, things like that, just constantly hitting the file system. And these are the producers. While this is all running 24/7, there's also a lot of consumers that basically would try and make a graph relationship though. So this crazy thing was basically a large directed acyclic graph on a file system, which you know you shouldn't do, but people do that anyways because they thought that because it was productive for the firm and the P&L was good. But throughout all of this, so this is constantly running and constantly happening. Have no issues whatsoever. So there's that. This one is a fun one. Another example, Lustre handled a very poorly high-intensity app that was, you know, maybe an app misconfiguration. But more or less what happened is if you have a large compute grid, you know, tens to hundreds of et cetera, 1,000 cores, what this app would do is it would start up, it would stat to see if a file exists. If it did not exist, it created it. And then it would open it with O truncate, write something very small, less than 4 kilobytes, and then close itself. Now that doesn't sound too bad, except if every single one of these threads does this many, many times per second. And what happened is like this workload overwhelmed 2 different NFS systems from 2 different vendors. And one of these NFS systems I actually like, and I think it's pretty good for metadata, but it does not have the Lustre kind of writability, namespace write metadata performance that you know that I kind of expect. So as I said, we kind of use Lustre for like a tactical debugging tool. We moved it to Lustre and said, hey, just run it. And the next slide is what I saw running it live. This might be hard to read, but I couldn't think of a better way to do it. So add 1 million open calls to this, but that's 3.9 million operations per second, which isn't that high of a number, but on Lustre, this is kind of a crazy thing that was happening, and it just worked. And the thing is, you could say, well, the numbers here and that. The important thing was we immediately saw what this application was doing and said, you guys need to fix this. On our other storage systems, like we didn't even see 10,000 set adders per second or something like that, because it screwed these things up so much that like you couldn't RPC throttle them or anything like that because you couldn't even tell what was happening. So again, a debugging tool, more or less. All right, so another example, Lustre handles deeply nested high concurrency metadata workloads well too. Our users are fairly sharp, and we tell them, don't write 100,000 files in a directory. They normally follow this. So what they do is, you know, we'll just create a kind of a GUID style or a B-tree style set of directories that are a couple levels deep, and then hash out where you're going to write your file to and go from there. A lot of our other storage systems cannot handle this very well, and I think it's simply because What our users do is they strive for correctness, which sometimes is more straining on a storage system. So essentially they do a make dir-p, but in Python. So if you give it a root directory and then there's 3 levels with, hexadecimal, something like that, kind of allocated, a make dir-p is going to stat all of those all the way down to the last part of the path and try and make those directories. If you have, 30,000 processes all doing that at the same time on the same top of the directory, that makes things very unhappy on a lot of storage systems. Works fine on Lustre though. And that's really testing the LDLM code though, because there's a lot of processes trying to simultaneously make the same directory if it doesn't exist. So there's a lot going on there. So this test I think is, or this workload I think is ubiquitous with us enough that I turned it into a very repeatable benchmark, and we use this for a lot of storage system evaluations now. So the bad news, well, it's not bad, but slightly less sad news, is Lustre ranked number 2 on this test. The number 1 system is just really, really, really good at certain pieces of certain metadata workloads. But the same system is the victim of some of the stuff I've talked about the last couple slides where it couldn't handle things either. But the thing that's interesting about that is this NFS scale-out system, the architecture for how it handles directories is very similar to what Lustre does with DNE3. So I think it kind of, I think the numbers kind of validate the Lustre approach here, and it's not surprising that the 2 best systems, by a long shot versus everyone else, happen to have the same kind of architecture for sharding metadata. So, yeah, there's nothing else there. Lastly, this is kind of a more vague slide. Look at the IO500 scores, especially with some of the newer releases. You can look at some of the entries, and you can see that people aren't doing a lot of tuning for metadata on Lustre. Just use DNE3, and everything is already taken care of, though, and you get really good scores out of it. I think we've all looked at IO500 before. I've also been greenlit to try and submit some IO500s. Hopefully I can get it before ISC, but we'll see. So, like everything else, Lustre has varied small file performance. It could be the best at certain things. It could be average, or it could be 20% slower. It just really depends on what exactly we're talking about. But it's no longer something that you can just assume it's going to be bad at everything. And to address, I would say, critics, and maybe they're not in the room with us, but on the internet or in the ether, someone's going to say, well, I know something that runs poorly on Lustre, and I totally believe you, because you can't get everything right. And there are certain codes that, when someone says, well, this runs poorly on Lustre, well, what does it do? Does it run? Maybe it just runs really well on NFS v3, and that's something that is totally true, and it's not. It's hard to fix. Think about say compiling the Linux kernel or something like that. When I've tested it, Lustre is faster at untarring and extracting the kernel contents than NFS-based systems. It's average at compiling the kernel and things like that versus some NFS systems, and 20% slower than some others. So there's a lot of varied performance that you have to think about here when you hear some of these claims. The takeaway is that Lustre is very competitive and it's always improving. I think that there's a lot of agility with the Lustre development model where you're not stuck with having to support what the NFS client does and that's it. So even 4 years ago, you wouldn't think that the distributed namespace stuff would just kind of work now, but that was a huge change, and Lamb Cloud just kind of did it, and it's in the code now. We have one slide for Lustre metadata design considerations. Some do's, and obviously this is kind of budget-centric and all that, but over-provision metadata storage if you can. Prioritize the capacity and performance for metadata over data capacity and performance. Some places that need 30 terabytes per second and that one extra 50 gigabytes, maybe that's not important to you, but I would say in general, metadata is very important for users, and if they know things run really well, then they're going to keep using it. And as I always say, an extra pair of MDSs I think is more important than an extra pair of OSSs, just because it's hard to fix performance when you have hardware constraints. And as we know with Lustre, like, it can be difficult to expand the systems, at least for metadata, so just be careful there. Optimized DNE round robin depth. This is just, by default, it's set to 3 when you build a new file system, which I think is fine. What we do is, we have a slash users or a slash projects directory. We set the round robin depth to 17, which means that after 16 levels within a user's directory, then it will use space balancing. I thought about just setting it to -1 and just do round robin forever, but I just never got around to it. I've always wanted to have a cutoff point where I can say, okay, I understand why this started happening here, because you made 15 or 50 directories deep, and that's just a little crazy. But the randomization for us, and we have multiple systems that have a ton of inodes and directories on there, have kept us within 2-3% usage across all of our MDTs. So I'm a big believer in just randomization. Some don'ts. Do not mix OSSs and MDSs on the same server. I'm not going to call out any vendors here, but one of them likes to do this, and do not do that. What happens here is that if you're doing a steady 100,000 metadata IOPS or something like that, and then you read at the max bandwidth of the adapters on the OSSs, you basically start to restrict metadata IOPS. So what you'll see is things will drop like a rock because there's all of the large RPCs that are kind of queued up. There's no QoS and things like that you can really do server-side to get around that. So if you're trying to build your own Lustre system, or if you have like some sort of elaborate NVMe or Fabric sort of thing happening, you might feel like, you know what, why don't I just put the OSS or the OSTs and MDTs on the same server? Don't do it. And this next point about data on metadata, this is kind of related. So, you might be thought, or you might say, it would be interesting to have a larger data on metadata stripe, though, because we can just put all of this, put a lot more data or a lot more blocks on flash. What you do is you turn your MDS into an OSS by doing that. So you should be trying to keep IOPS off of your spinning disks, not trying to get a lot of throughput on your metadata servers. And a good example, just look at what the Oak Ridge PFL setup. So it's data on metadata, a small PFL stripe on flash, and then everything else on large OSTs. All right, I don't have a lot of time left though, so the Lustre wish list. Faster failover and recovery. We have some workloads at the firm that run like crap on our NFS systems, but our users say, well, it probably runs fine on Lustre, and we know it runs fine, but whenever Lustre has a failover, it could be a small percentage of the namespace hangs for 3 to 5 minutes, or it could be a little bit less, just depending on the number of outstanding transactions. Taking that to like less than a minute would help things immensely. Now, someone here could make the argument that says, well, having 5 minutes of partial namespace downtime once every 3 months due to a failover, like, that's not really that much time, and the rest of the 3 months, you've been getting a lot better performance. I understand that, I agree, but it's not my decision, and a lot of people do not think about things like that. So just a perception that having a 1 minute failover or less than 1 minute failover goes a long way. Improve metadata and data management. What I mean by this is expanding file systems, things like that. I'm not going to name drop any competitive file systems, but I think the other long-standing parallel file system has really great utilities for shrinking and growing storage, and it would be great if things like that were in the Lustre product, because I've shrunk and I've grown file systems myself, and it's kind of a hairy situation. And I've worked with this stuff a while. There's a lot of people that, when you think about overall adoption, that would have no idea how to do that. And it's just a very daunting task, though. So having some of the stuff more built into the product, I think, would be nice. Flexible storage with FLR and erasure coding. This is kind of a wish list, because at the end of the day, I would love to be able to buy 100 servers with NVMe in them and just have no dependencies on anything else though, and just run Lustre on that. And native HA stack, curl sync and pacemaker I think works pretty well as long as you tame it. But at the end of the day, like if you mix this in with FLR, do you really need failover anymore? If basically you just say, well, the server died, just redistribute the blocks, you don't have to do any failovers, as long as you hit all the transactions and things like that. So, summary. In closing, I'm always going to say this: fix your code if you can. Just because you can do a million file creates per second doesn't mean you should. Try and fix the code if you can. Open source wins again, as always. Lustre's been at the top of I would say the HPC food chain for quite a while, and it's just because of the community and all the contributions from all the different firms and things like that. I think part of this is because of the strong, very initial design of Lustre, and this is like 1990, 2000, things like that. And now, as it's been said, Lustre is kind of expanding a lot outside of just HPC. So there's a lot of large AI systems and things like that, though, that are utilizing Lustre very heavily. And the other thing I'd like to say is the competition comes and goes. I've heard this for a long time. The Lustre architecture is outdated. Oh, really? It's based on objects, and everyone loves objects now, and it's been like that longer than anyone else could think of. It's not built for Flash. Do the people that write the software not understand how hard disks and flash drives work and how to optimize them? And it's too brittle. I can kind of see that, but I don't think it's brittle. I just think it's a little bit kind of a pain to use until you get used to it. And the most important thing is Lustre versus a lot of other things has been battle tested at scale versus most other solutions. There's not many things that are in public use that can scale the same way Lustre does and handle everything. And finally, point of the talk, Lustre is quite good at small files and metadata performance now. It's time to stop saying otherwise. So next time you hear someone say that, just say, nope, that's wrong. Questions?
Thank you very much, Stephen. Any questions?
So you mentioned a lot of comparisons between Lustre, community Lustre, and you allude to it, GPFS. But as for configuration, like, do you unutilize MDT0 and redistribute your DNE3 to the rest of your MDTs, or because that tends to be a brittle point as you come to, right? MDT0 goes full and users lose their mind.
Right. I think my main pain point was that, and maybe this is just something that where I work now needs to do things a little bit differently. Like, I know traditionally with Lustre is like you spec the system out, you buy the whole thing, and that's what you're going to use for 5 years. You normally don't kind of expand the same namespace and all that. What we would like to do is like say, hey, we have a 10 petabyte system or something like that, and we would like to double the performance and the capacity. It's not too hard to do that from a OST perspective, though, because you can kind of creatively get around like the performance when you kind of restripe things or set the weighting. But with metadata, like, does anyone here have the guts to like restripe like a couple billion files across new MDTs and things like that? Like, it's not an easy operation, and like a lot of things can go wrong. And if you look at the mailing list, like there's been bugs with that before, though, so it's something that I think needs to be improved.
We unfortunately overstriped 90 billion files on a DNE 2-based file system due to misconfiguration and migrated it. And I'm pretty sure Andreas has a script to do it. Because he gave it to me.
I mean, I don't know, like, I've read a lot about this stuff, and it does not seem like it's a very easy operation.
Was wondering if you could share any of your best practices with respect to managing metadata servers, like the number of servers and sort of how many IOPS per server or how many files per server, et cetera.
I don't know if these are agreed upon community best practices, but, and again, my systems are Ethernet though, so when I say some numbers, these are gonna be for Ethernet. InfiniBand is gonna be a little bit better. We try and keep about a billion inodes per MDT, and we kind of assume that each MDT can do about 200,000, maybe 150 to 200,000 get adders per second, and then everything else is going to be less. So I don't have the exact numbers in front of me, but the biggest thing on our systems is get adders. That or bursts of creates or something like that, though. So unfortunately, I don't have a better answer than that besides 150 to 200,000 get adders per MDS, which I think that's like double that with InfiniBand, by the way. So that's kind of the rule of thumb there, and then a billion per MDT. And that keeps you from having to do like any sort of MDT management because you tried to size it too low and kind of squeeze pennies, if you want to call it that.
I was just going to back you up that, yeah, it's way easier to add metadata in some competing products than as someone that's currently doing 30 million restripes. Yeah, it's a bit easier to, especially if you have to do anything with that MDT0, which is certainly on the roadmap and getting addressed. But
yeah, I mean, so what we tried when we first got one of our DNE systems, we bought X number of units, and we were using a couple more units as like a POC. So we said, okay, we'll buy the new system, and we're going to put everything in production on these new units. Then we're going to repurpose the old units because they're the same exact sort of SSUs into our system. Well, a couple of these units had no files or no uses on the OSTs and no uses on the MDTs. The OSTs, you can kind of you can kind of just get over it. With the MDTs, it took a long time to slowly get close to the number of files and balance that, even with randomization. And we tried all sorts of tricks where we purposely created a bunch of directories and pinned them to certain MDTs with a bunch of files in them. And then after every couple days we would delete one of these directories. It's really hard to get that balance back. And the only way to really do it is not outside of some cowboy thing I just mentioned. The file system has to kind of do it itself.
I just wanted to do a +1 on your statement to reduce recovery time. So with Merced and 240 OSTs, your MTBF numbers mean something's always going into recovery, and each one of those means the whole file system may, hang, if you've got data striped across lots of OSTs. And so it gets pretty disruptive for, consistent operation of the file system. So I don't know what's physical, what's possible, right? You're still dealing with physics, but if we could somehow drop recovery time significantly, it would be a huge win for us.
Yeah, it's one of those things where it just sounds like a really easy statement, yeah, just make it faster. Obviously it's very difficult to do this, and the reason why it's so easy for NFS to do a 5-second failover, because it just does a gratuitous ARP and moves the IP, is because it's not POSIX compliant down to the cache on the clients. So that sort of feature is hard to make it possible, and there's a lot of things happening that's required to be that consistent and atomic. Uh-oh.
No, so an interesting question about, do you have to actively rebalance the MDTs versus passive rebalancing? Because you're saying, you added in these MDTs, but if your MDTs are over-spec'd anyways, you're adding in performance because you're distributing your new directories and workload across more MDTs, and having the old files is not worse than before you added the extra capacity. So as long as you're not right at the edge of 95% of using those other MDTs, is there a hard demand for rebalancing? Or is it just because you like the numbers to be even?
I mean, that's part of it, but like what, part of the, like, we have, like, I showed that slide before where it was like, this is the live snapshot of like basically Lustre top or something like that. We kind of rely on the performance because it's so well balanced across all the systems though. So if we were to add completely new MDTs and immediately we'd have the same balance, so any new file creates and all that would be I don't want to say striped, but allocated across even the new MDTs evenly, it's probably okay, and then you can just kind of hope over time as the old stuff is deleted, if it's kind of a heavy transactional use system, then maybe it'll balance over time. But what we have found is that sometimes like the space balancing is either too aggressive, so you kind of have to tune it. Like it's just kind of tough, you know?
Okay, no, it's legitimate. The other thing was about the failover time. I mean, obviously, you know, we're looking to reduce that, you know, as much as possible. I think it's going to be kind of a two-pronged approach, right? One is going to be actually reducing the failover time, you know, recovery and everything like that to be faster. But I think, you know, things like erasure coding or, you know, MDT replication above the storage device is going to be, you know, another way to tackle that problem, so that if you have, let's say, a read-mostly workload and you have erasure coding or mirroring of your files, then you don't have to wait for the failover, so the time that it takes to recover is going to be irrelevant, right? And so it's not, you know, it's not a perfect thing. I think, you know, GPFS has, you know, VDEV failover, and it can be done in, you know, fractions of a second, but because it's a totally different, you know, I/O
Right.
model, and so we have stateful clients, and you can get, you know, some of the performance and things like that are based on the fact that, you know, the clients understand, you know, or can handle a lot of more complexity, and they don't have to synchronize everything to storage all the time, and so, you know, you win 95% of the time. I don't know. You said, you know, we win 95% of the time, and then, you know, 5% or 1% or whatever, when we have a failover, you have to pay that cost a little bit. And so I don't think we can totally get away from that, but I think we can attack it from a few different sides.
Yeah, I mean, it might just be as simple as just making a nice sounding number. People like to hear, oh, less than a minute, that's probably not too bad then. And the thing is, I think at least where I'm at, we kind of understand the benefits of not having to consistently or constantly synchronize via NFS v3 to the storage though. So like, when we originally spec'd out one of our first systems, we said, well, it has to do 3 million get adders or something like that. That's only like that on NFS because it has to constantly update the directory contents all the time. And like, so we don't need to do the same things on Lustre. So because of the client-side cache and all that. So I think we kind of understand the benefits now, even if like we find it a little bit painful here and there.
As someone who's not yet architected a Lustre file system but has helped to administer one, I'm always interested in the volume to inode ratio. So I saw you said 25 billion inodes. What was the volume of that system?
Volume in terms of like...
how many petabytes?
I cannot give a lot of facts and figures, but I think this is kind of an old one, so hopefully no one's listening that's going to get mad at me. But this was only like a 2.5 petabyte system.
Okay, yeah. I'd be
But like
curious.
that slide I had earlier was actually the MDTs from that system though too.
Wow.
So like we kind of like said, okay, we want to get a lot of performance, but also we want to have a lot of metadata performance. So we kind of overspec'd our MDTs, and like it's worked out for us.
Well, thank you very, very much.